she's got so much rich experience of connecting mathematics with the real world. You've also been involved in this an interesting project here. In your bio, it talks about this New Life for Haiti, where she manages the child sponsorship program that provides an opportunity for children who otherwise could not afford to attend school. So really has done some very interesting things with her life. When we were talking a few minutes out in the hall, she was also telling me about another project that they've undertaken where they're really directly engaged with kids to really try to make these connections with engineering. And she's especially interested in connecting girls and women with engineering, because our stats don't look very well, ladies. And we really need to work on that, gentlemen, and encourage more people. So she is also on the Associated College of Illinois Board of Trustees. So she comes, with so many different rich experiences. A very busy lady. We're so pleased that she was able to take time out from her busy schedule to be with us this afternoon to talk a little bit about the connection between mathematics and engineering. So please give a warm welcome to Erin.
So let's see if I can move this.
Oh, there you go.
Thanks for that introduction, and good afternoon. I'm really happy to be here today. So I'm going to give you a little bit of my background and how I got to where I am, and then I have some project examples so you can kind of see the problem solving that we look for from our engineers. And at any time during that, if you have a question, just very informal, shout it out, and we can get going. So Marie Curie once said, "Nothing in life is to be feared, it's only to be understood." She was the first woman to ever win a Nobel Prize, and the only person in history to win that in 2 different sciences. So how do we get kids excited about science and excited about solving problems and looking to engineering and science for careers? My path to engineering was a little more challenging than most of the guys that I work with. I was good in math and science in school. I liked solving problems, loved high school physics. So engineering seemed like a more practical way for a career than physics did. So I went to see my high school counselor, and she discouraged me from engineering. She said, "Girls don't do that. Why don't you look for something in the liberal arts?" So needless to say, I applied to engineering school anyway.
Yes, bravo.
There were 120 people in my engineering class when I got there. There were only 4 of us that were women. So little did I know that that was just the beginning of the challenges that I would face. So I had an assistant professor my freshman year that would not allow me in class, said he would not teach women.
Oh my God.
So after a little discussion with the dean, he found something else to do. But there were just lots of, why are you here? We don't need girls in this. And it was just much more challenging than I expected when I went into engineering. And when I graduated, I went to work for the U.S. Army Corps of Engineers at a construction field office in Texas. It did not occur to me at the time that this was not going to be a very woman-friendly work environment. So I was going to be working on construction sites, making sure that the contractors adhered to the design standards and designing any field changes that needed to happen. So I was the first woman that they had ever hired in that office. So if you can picture this, I show up to my first day of work. All the guys in the office are in their 40s and 50s. I am 22 years old, jeans, hard hat, hair in a ponytail, right? I look like I'm about 12. So the section leader was great. He took me around, introduced me to everybody, got my first project assignment, and I'm thinking, this is awesome. This is exactly what I want to do. And then he said, we need to have an all-hands meeting. So we all went into the conference room, and the section leader said, you've all met Erin, our new electrical engineer? And everybody said, yeah. He goes, we need to talk about the bathroom. And I'm like, what? So our office was in an old World War II building, and it was built with only a men's room. So, as he's going on about, this issue that we need to discuss, I'm turning 6 shades of red. And he's telling the guys, listen, you're gonna have to shut the door when you go into the restroom. If the door is closed, you're gonna have to knock. And I'm thinking, can I crawl under the table? So, but we got through that, and, got through my first day and came back for my second day, which was my first day on a construction site. In the early 90s in Texas, there are no women on construction sites. So it was a challenging day, but I was determined that I was going to make this work, and after about 6 months, it was all good. So after 5 years in that field office, which turned out great, I took a job in Chicago as a design engineer. So I'm thinking this is going to be a much more women-friendly work environment, which it was, but there were still plenty of meetings that I walked into and had people ask me if I was the engineer's secretary. So what an awkward moment it was for that guy when I said, nope, I'm actually the engineer. But, again, that's starting to get better. I'm happy to say after 20 years, things are better, but there's still only 11% of the engineers in the workforce that are women. So, which is still not a whole lot. So, what is engineering, and is it really all that important? Engineering is the practical application of science and math to develop ways to utilize the materials and forces of nature for the benefit of mankind. So engineers are inspecting and designing everything that we use every day. There are engineers inspecting the bridges that we drive over. When you turn on the water, there are engineers that are working at the water treatment plants, at the pumping stations, at the sewage treatment plants. When you turn on a light in your house, there's thousands of engineers that work to generate that electricity, that do the transmission, that get that energy to your house. So without engineers working every day, all the conveniences that we take for granted would start to have issues. So why can't we outsource this to India or China? Much of what engineers do actually involves going out in the field and looking at things. So if a truck hits a bridge, you need a structural engineer to go out there and inspect that bridge and determine whether or not it's safe before anybody drives over it again. If we have a storm that rolls through here and trees take down the power lines, you need engineers to determine how we're going to reroute that power while those power lines are getting fixed. Otherwise, you're out of power for days and days. So my specialty is in power engineering, so we'll dive just a little bit deeper into that. According to the Center for Energy Workforce Development, by 2015, approximately half of all the utility workers and trained engineering staff will be eligible for retirement. So in real numbers, that's about 7,000 engineers. Nationwide, we graduate 900 power engineers a year. So unfortunately, the math just doesn't work out there. Not to mention that, we're talking about engineers with 30 and 40 years of experience that are retiring, that can't be replaced by someone just fresh out of college. And to exacerbate that problem, the increase in renewable energy, electric cars, smartphones, iPads, flat screen TVs is creating a tremendous demand on the utilities right now. Utilities have never been busier building new transmission lines, installing smart meters, automating the smart grid, and trying to upgrade a power system that's over 100 years old in most places. And all of this is happening, nearly doubling the demand for engineering at the utility companies when they're facing, just a critical retirement, just an exodus of their knowledge base. The consulting industry, which I'm part of, is also feeling the effects of this. So after a flood of retirements 2 years ago, the utility in Northwest Indiana decided that they would outsource all of their engineering. What they had left of their engineering staff would become project managers. Our work with the local utilities has tripled in the last several years. And that means that we are competing with utility companies and other consulting firms for the same very small talent pool that's out there. So what skills are we looking for in new engineers? Clearly, technical knowledge is important. You have to understand how electricity works, how it flows in power systems, but that's not enough. As engineers, we're given problems to solve, and we have to do it within the boundaries of engineering practices, the national codes and standards, and then the client standards for construction and operation. So, let's see if I can. About that. So this is a typical project diagram that we're given from the utility industry. So this tells us how the project's supposed to be electrically connected. What's in red is what's new, that's what we're supposed to design. So this doesn't tell you a whole lot. We can go into utility maps and we can look up, the 7201 RS and figure out where that's at, and we can look up the K336 and find out where that's at. Well, when we do that on this project, that's 8 miles apart. So we need to run new overhead power lines 8 miles to connect those 2 points. So the utility doesn't tell us how to get from here to there or what we need to do. They say our mandate is least cost. So you guys figure out the least cost solution to get from here to there and connect this. So we need to look at, the first place we probably go after we figure out where these are on the maps is Google Earth, right? Let's see what we see out there. Are there power lines there already? So if they are they, you can put 3 circuits on a power line, so how many circuits are there? If there's not 3, then maybe we can just reuse the poles that are there. If that's not the case, maybe we have to get a new easement. So we have to work with whoever the landowners are to figure out if we can get a utility easement there. The problem with that is it's expensive and it takes time. And we have a deadline. We got to get this project done. So on this particular project, that first section is 8 miles and the bottom section to the new ESS is another 7 miles. So that works out to be about 400 utility poles. So once we figured out what the path is and where we're going, we actually go out and we take a picture of every pole, take field notes of what's there. So we get to get out of the office, which is very cool, and look at that. So this pole, for example, is a 35-foot tall pole. It's got a 12,000 volt circuit on top, a transformer, and then a secondary circuit below that. We need to install a 34,000 volt circuit. So that has to go on the top, and the standards tell us we need 7 feet of clearance. So that means we need to change out this pole to a 45-foot pole, put all this stuff back on it, and then run our circuit on top. So we're doing this at 400 locations, and we may have places where we get that the poles are already full. So maybe we have to go underground for 200 or 300 feet and then pop up on the next pole. But we need to look at every single pole along the path and evaluate how do we get this done. So we know this project, for example, is for ComEd. So we know what ComEd standards are. We know how they build a pole. We know, what our project constraints are that we have to get from here to there. And we know that we need to do it for the least cost. But other than that, it's up to us to figure out how to do it. And then draw it up and present that back to the utility and say, here's our solution. So, we're looking for kids that can problem solve, right? Because they're not going to teach you in school how to figure this out. They'll teach you what you need to know about electricity and how to build a pole, but then you need to figure out how to make it work. So this is another typical project. This is Route 83 and Rollins Road in Lake County. So if any of you have ever been up that way, Lake County Department of Transportation is going to do a grade separation, right? There's railroad tracks that go right along Route 83, and they've decided that it would be safer to do an underpass under the railroad tracks. So they're going to drop that intersection 30 feet. And this section right here, all the way across, is a ComEd right-of-way. And there is a ComEd substation that's just off the screen there. So there are 15 circuits that come out of that substation that feed most of Lake County. They go through there in, so they cross underneath Route 83 in a 36-inch steel casing. When Lake County gets done excavating that, it'll be about this high. So that really won't work going across the road. So we need to move all of that before they start construction. And we get the roadway plans. So we know they're going to put in temporary roads. You know, everything that's shaded is everything that's moving around. And we need to move all of our stuff and stay out of their construction areas. And we need to get it all moved before they're ready to start construction. So the first thing we need to do is figure out what's there right now and get it drawn up. Oh, and first we have to go out and look at it, right? So this is the picture from inside a manhole. So you get an engineering degree, you get to go into manholes. And if you look at the bottom of that, it was full of water. So we had to wait for 45 minutes while they pumped all the water out of there. So it's kind of dripping and nasty. Doesn't really smell bad though. But these are the power circuits that are going underneath the road. So we put together an existing conditions drawing. So we've got the railroad tracks, we've got the street, the right-of-way, all the circuits that are going under the street. So that's kind of our starting point, right? We know where everything is. Now we need to coordinate with the construction contractors to find out how are they facing this? What's the first thing that they're going to tear up? So what's the first thing we need to move? Because you can't just say, all right, we'll cut this off and we'll build the new and then we'll pull it all through the new one, right? Because you're not going to get all the businesses up there to say, oh yeah, a month without power, I'll be fine. Right? It's all got to be, all the new has to be built and then you cut it over overnight so that nobody loses electricity, because nobody's very patient about that. So while everything is there, we have to coordinate with, you know, what else is there. So NICOR has a high pressure gas main that goes through there. Well, we can't be in the same space that they're in. And AT&T has a 1,800 pair of fiber that goes through there. That's pretty much everybody's phone and communications. So we can't be in their way. We need to stay within the right of way because that's where ComEd has space. And we need to not be in anything that the contractors are going to need for construction. So it gets to be a big puzzle, especially this job was about 1 square mile that they were tearing up. And there were areas where they said, you can be in this foot, you know, and I'm like, well, you know, that's not really going to work. Even a pole is not going to fit in that. And they're like, yep, sorry. You know, figure it out, but you guys can't be in here. So it was a big puzzle. We worked on this project for probably 4 or 5 months to figure out how we're going to move all these circuits out of the way and do it where they can be digging up the road without digging up anybody's power line.